Hi, folks. Today, I just want to take the next, say, 30 minutes or so to do a quick introduction to how to do numerical simulation or integration of dynamical systems models using a simple spreadsheet tool like Google Sheets or Microsoft Excel. Now, formally, what we're doing is something called Euler's method of numerical approximation of dynamical systems, but practically what we're doing is what happens behind the scenes when we go into Vensim or Insight Maker or Stella or AnyLogic or any one of these system dynamics modeling tools. And we draw a stock and flow diagram. And after drawing it, we set a simulation time step and we hit run. Behind the scenes, those programs turn those stock and flow diagrams into systems of differential equations, which mathematically, if we have the right analytical tools, could turn into smooth curves that you could write out in a functional form. But the computer, instead of solving it in the symbolic analytical way, it makes an approximation. And it does that by chopping up time into time steps so that it can estimate what the differential equation would look like at a particular time step and use that to then guess what the system will be at a time step a little bit later. It'll estimate the differential equation at that time step will go a little bit later and so on and so forth. And as long as these time steps are really small, then the resulting approximation, which will end up being a bunch of little lines pasted together, will look like the smooth curve that you'd get if you solved it mathematically. That's what Euler's method really does, is it turns these smooth curves into lines. And behind the scenes of what's going on in Vensim, Insight Maker, et cetera, is that it's doing these approximations for you. And that's what we're going to do manually here so that we really can appreciate things like the time step and what they are and so on. So in order to do that, I am going to do a simple bacterial simulation example. So I'll put that up here. So by the way, I just went into Google Sheets. I created a new sheet like Google Docs, new sheet. You could also do this in Excel and pretty much everything will be almost exactly the same. And at the end of this, I'll show you how to export your Google Sheets into an Excel and deal with some of the chart artifacts that happen when you do that importing process. But so at the top of this new spreadsheet here, I'm just going to call this my bacterial population example. And what I mean by a bacterial population example is imagine a population of bacteria that are asexual and clonal. And so we could go to a microbiologist and we could ask them for a number of parameters that would characterize this species of bacteria. And let's say those parameters might be the average time it takes for a particular bacteria to wait until it reproduces and the average lifetime of each particular single bacteria. So the idea would be that if I were to watch a particular bacteria until it pops and becomes two bacteria, then that might happen, let's say on average, every 3/4 of a minute. And so that would mean that several reproduction events will be less than 3/4 of a minute apart, but a bunch of reproduction events will have to be more than 3/4 of a minute apart. And so on average, every reproduction event, every time it duplicates, will be about 3/4 of a minute apart. Likewise, we can ask how long is each individual bacterium alive? And we can say, well, the lifetime average is about 3 minutes. And so then that would mean that there are bacteria that live for less than 3 minutes, there are bacteria that live for longer than 3 minutes, but on average, we use 3 minutes. And so we're modeling the average population dynamics, knowing those averages. How, on average, how quickly does each bacterium double? And on average, how long does each bacterium stay in the system before it dies? So that's what we'll specify up here. And so what we're going to do is in the first couple of cells of this spreadsheet, we're going to specify what those are, those exogenous variables. And so those are variables that are set external to the system. They're taken in as constants to the system where we can change them in one place and we can see how it affects the system, but they themselves cannot be changed by the system. That's what I mean by they being exogenous variables. In order to make them more compatible with the mathematics of how the differential equation unrolls, we'll also create several converter variables, which just convert them into a form which makes the further expressions a little bit more compact. And then we'll actually then have the simulation where we'll end up having every row of the simulation will represent one time step in this numerical simulation. All right, so that gets us to a first exogenous variable, which really has nothing to do with the bacteria at all. It'll be in every one of these numerical simulations, regardless of what you're simulating, the simulation time step, which I'm going to call dt here. And so I'll put a little description over here, and this is the simulation time step. And for this one, I will take it to be 0.01 time units. And so by time units, it's whatever time units the microbiologist gives us the parameters in. So let's say they were in minutes, like in the description that I just gave you, then I'm putting this in hundredths of a minute. So then I go down and I say, well, the microbiologist told me that there is a waiting time, an average waiting time until the bacteria duplicates, until each bacteria has a reproduction event, which I'm going to call W for waiting time. And I'm just going to say this is average time between reproduction events for a single bacterium. And I said it's about 3/4 of a minute, so I'll put 0.75 there. And then I have the average lifetime for a single bacterium. And I'm going to say it's about 3 minutes. Now, differential equation systems are usually specified in terms of rates. So system dynamics models are more convenient to be expressed as rates. And these times are not rates. And so I'm going to introduce some converter variables that make it easier for me to express them as rates. And so I'll create a reproduction rate, make this a little bit bigger. And this reproduction rate, we can think of this as the number of reproduction events per unit time per each bacterium. So this is just the reciprocal of the average time between reproduction events per bacterium. So I'm going to hit equals 1 divided by, and then click on that cell where it comes up to be B2. So again, just the kind of logic here is that we know that we get a reproduction event per bacteria every 3/4 of a minute. If we want to turn that into a rate, then we have one event per 3/4 of a minute. So that's where I get that reciprocal there. So every bacteria is contributing this number of reproduction events to the total population. So that's why it's per each bacterium. Now, if I hit enter, it'll do a calculation there. But notice that this expression here says 1 divided by B2. Because I want, so in these spreadsheet programs, there's something referred to as relative referencing, which is what we have here, and then also absolute referencing. And so in relative referencing, if I were to take this cell and copy it and paste it somewhere else, like over here, then if I were to see what the formula looks like over here, then I can see that it is trying to take the reciprocal of this empty cell. And that's not what I want. And so what it did is it looked at the formula over here in this cell, B2, and when I copied that formula, it saw that it was displaced by this number of columns, so from column B to column H. And so then what it did is it took all of the relatively referenced cells in the formula, and it shifted their column over by the same number of columns. And so it was originally a B, and now it is an H. Now, because this special exogenous parameter, this constant, never moves, then whenever I refer to it, I want to use absolute referencing. That way, if I copy the formula somewhere else, it still refers to that same spot. So the way I do that is I go to this formula, and instead of doing B2, I can put $1 in front of both of those things, and that makes both the row and the column absolutely referenced. So now it calculates the same thing there, but if I were to copy that and paste it somewhere else, then the formula stays put, or at least that cell reference, B2, it stays B2 in the target after I've pasted it. So that's good, that's what I want there. Now, before I move on, I just want to show you a little trick there. I can manually type in those dollar signs, $B, $2. Or after I've maybe clicked on this cell where it says B2, in both Google Sheets as well as Microsoft Excel, there's a hotkey that allows you to quickly toggle through all of the absolute reference modes. And so I can hit F4 to do that. Now on a Mac, like my Mac here, on my keyboard, I have a row of function keys across the top, but those function keys don't default to their function. Instead, if I were to hit the key that's marked F4, it would do something else related to my operating system. So on my system, and it might be different on yours, I have to hit the Fin button first, and then hit F4. And you see when I do that, it changes the B2 to $B $2 for me. If I were to hit F4 again with function pressed down, it changes it to B $2. If I hit it again, $B2. And then if I hit it again, it gets rid of all the absolute referencing. So I'm just going to go back to the $B $2. So that's a quick way for me to turn a relative reference into an absolute reference. All right, now I need to do the rate of deaths per individual bacterium. So that is going to be 1 divided by the lifetime. And I'm going to do my function F4 there. Oh, see, I accidentally did not hit down function. I'm going to hit function F4. And then that will change it to a $B $3 as I wanted. And that is the number of, we call it death events, or I could say bacteria removals per unit time per each bacterium. So that's really what a death is in this modeled system. It's the removal of a bacteria. And so I'm saying that each individual bacteria dies after an average of 3 time units, let's say 3 minutes. So we model each bacteria contributing to the outflow as this 1 divided by lifetime number, and that's what we get there. So now I can actually put the columns in my simulation. And so I need a time column to keep track of what time step we're on, a bacteria column to keep track of the bacterial population per time step, and then I need my inflow. In this case, my inflow is my number of reproductions. So I'll just call it reproductions and deaths. Now the time always starts at time 0. The number of bacteria, in this case, I'm going to assume I start with 1 bacteria, but I could start with 100 or whatever. It's my initial condition of this stock. That's really the bacteria is the stock. And then now I need formulas for the number of reproductions and the number of deaths. Well, for the number of reproductions for this time step, it's just going to be the number of bacteria, I just clicked on that, times the reproduction rate per bacteria. And then that I want to be an absolute reference because I'd like to be able to eventually fill this down so that this formula can be copied into future formulas below. But when that happens, I want every single formula to use B5 for the reproduction rate, even though the number of bacteria will be from that row. So I'm going to do function F4, and that changes it to $B $5. And that'll make it so that when I fill this down to the next one, then that B9 will automatically change to a B10, but the B5 will stay B5. Then for deaths, I do a similar thing where I hit equals, and then the number of bacteria times the number of deaths. And then I can hit function F4 to change it to the absolute referencing, and then I'm good there. So those are my inflows and my outflows for this time step. Now I need to update the stocks for their next time step. So time is kind of like a special type of stock where it's going to be the previous value of time plus our time step. But that too needs to be an absolute reference. And so notice that now my time goes from 0 to 0.01. And if I were to grab this little fill down handle and drag it down, then I can see that it goes from 0.01 to 0.02 to 0.03. It keeps moving in these steps of 0.01 up here. Similarly, for bacteria, I need to do equals, and then the number of bacteria plus, and then I do the time step again, similar to how Google Sheets is guessing that I want to do. So I'm going to, I could take its tab to accept, but I'm just going to click up here and then I'm going to do my function F4 to change that to the absolute referencing. But now, because this is the number of bacteria, I need to scale the time step by the inflows minus the outflows. So I'm going to do open parentheses for open quantity, and then I'm going to do all of my inflows as positives. So there's only 1, reproductions, minus all of my outflows. So if I have multiple outflows, I do minus outflow, minus outflow, minus outflow. So basically minus the sum of all the outflows. And so the outflow here is the deaths here. And then I close parentheses. And if I hit enter, then that tells me the number of bacteria in the next column. And so now I just need to fill these things down, and I need to do that up to my 5 minutes. So before I go all the way to 5 minutes, I want to show you a couple of tricks for filling here. So this bacteria column, Google Sheets knows that there is a time column next to it that goes down this far. So what I could do is I could manually drag this fill handle down here, and it would fill that down. And because the flows aren't populated, that's why this looks like all like 1.01. That's one way to do it. But the other thing that I can do is if I have, in this case, a group that I want to fill down, and I can do this for an individual as well. If I go to that fill handle, instead of dragging it down, if I just double click on it, then it automatically looks at the columns next to it. And if it sees that there's a column that's much longer than the others, it takes your columns and it fills them down to that length. So that allows me to quickly fill down without dragging. And that works for both Google Sheets and Microsoft Excel. If for some reason it's not working for you, you can always grab that fill handle and pull it down. Now, the other way that we can fill down is if you click on a cell with a formula, it has to have a formula in it. It cannot be one of these initial cells here that has a constant. It has to be a cell with a formula in it. Then I can hold down Shift, and I can click on a cell later on down here, and it'll highlight all of those cells. And if I then on a Mac hit Command and then hit D, or on a Windows machine, Control and D, then it will then fill down within that highlighted range. So this is handy because it allows me to extend my time column. And then once my time column is extended, I can highlight across all of these and then double click their fill handle and it'll fill them down. Now in this case, I want to do my simulation all the way up to 5 time units. And this is only getting up to 0.17 time units. So I got a lot of ways to go. So if I look up here and I think, well, a simulation time step is 100th of, let's say, a minute. If I want to simulate for 5 minutes and my time steps is 100th of a minute, I need 500 cells for those 500 time steps. So I start in row 9. I want my last row to then be 509. So what I'm going to do is I'm going to click on the first cell with a formula, or any cell with a formula, in my time column. And then I'm going to scroll down to row 509. And I'm going to hold down Shift, and I'm going to click on this so that I get that full column selected here. And then I'm going to hit Command D on my Mac, or you can hit Control D on Windows, and it would fill that down. And then look, the time here is 5. Now, if for some reason I did my math wrong and I overshot some or I undershot, so if I overshot, I could then delete these cells. If I undershot, let's say I ended up only going to 4.96, I could click on the last one and then pull it down until I got all the way to where I wanted to stop. Now that I've done that, now I could have done that for that whole block of 4 cells, but I wanted to make sure, I got my timing right. So now I can go up here, I can click on these 3 across, can double click on that fill column, and it will then fill down all the way to row 509. Again, I could have dragged across these 4, and I could have just filled them down all the way from the top, but it was just a little nicer to fill the time down and then double click to get the rest of those down. All right, good. So this looks like I've simulated my bacterial system. Now I just need to plot it to see what it looks like. So I'd like to plot the time column against the bacteria column. So I'm going to click on the time column header, and then I'm going to scroll down, and I want to shift click on the last row of the bacteria column. So if I do that, I go down here, and here it is here. I'm going to shift click there. So it highlights this rectangle from A8 to B509. And if I go up, then I'm going to scroll to the top. So that's important. Scroll to the top. And then I go to Insert, Chart. And then it will put a chart roughly where my mouse is. And so my chart is going to obscure it's going to get in the way a little bit of my flows here. You should probably move yours over here, but I'm just allowing it to see it in my share view here. And that gives me kind of a curve, just like I was expecting, sort of an exponential growth curve. So that's great. What I don't like is in this axis here, it doesn't show that I'm going all the way to 5. So what I'm going to do is just click on that axis here. And it brings me into this chart editor and over in this customize tab. And if I scroll down here, and then I can, in case you can't see it, there's a min and a max under horizontal axis. So I click on customize. It's got a bunch of different things customized. Make sure into the horizontal axis pull down here, expand it. So horizontal axis, expand it. And then under the horizontal axis, it's got a min and a max. And I can set the max to 5, and it makes sure that it's going to bring it all the way to 5. So that looks pretty good to me. So that's a good looking chart. I can move it over. If I would like to export that into a Google Doc or a Word doc, then I can go up to the edit menu here, and I can go to copy. And so you could, let's say I'll bring up a Word document just to mix things up a little bit. So here's a Word document here. If I now go to edit and then paste, or use my hotkey for that, then I bring the chart in, and it looks pretty good inside Word. Because ideally, when you're reporting on these things, both scholastically, like in your classes, as well as professionally, you do not want to dump into a document a whole bunch, hundreds and hundreds and hundreds of rows of numbers. The chart is meant to be the exportable deliverable that helps someone else see the output here. And so that's why we bring the chart into the document. Now, the thing is, though, that if in like my courses, I also have students not only upload their documents, and so you might probably have a document here, and I'll have you add text around it, like a caption around this thing, maybe a description of what's going on. I may have you answer a few questions and so on, and all that will be written in the document. So the figure will be in line with your text and all kind of together. But I'll also ask you to upload a portable spreadsheet version that kind of sort of show your work, so that if I do need to look at your spreadsheet, I can take a look at it. So if you're using Google Sheets, the easiest thing to do is to export it as an Excel spreadsheet and then upload that Excel spreadsheet. Now, one of the downsides of doing it that way is that when you export a Google Sheet as an Excel spreadsheet, sometimes it messes up the chart formatting. So let's see how to deal with that. So I'm going to go to File, and I'm going to go to Download, and then say Microsoft Excel. It's going to say, where do you want to save this? And I will save it over here as an Excel spreadsheet. So I'm going to open that up in Excel. I'll bring this smaller so that we can see it inside my little shared window here. And what we can see now is that it pulled in everything that I put in together in the Google Sheet. That's great. But the chart doesn't make a whole lot of sense. Like it's, and the reason is the horizontal axis is kind of all wrong. And so, and if I click on the axis and double click on it, it doesn't quite show me the axes format or the axes settings that I think I'm looking for. So what I usually do when I bring things in from Google Sheets into Excel, the first thing I do with my charts is change the chart type, because usually changing the chart type is a way to get it into the right format again, that you can start editing the chart options inside Excel. So if you click on the chart, hopefully it'll bring you directly to the chart design tab. If it doesn't, you can click on the chart design tab up here. And then you can say change chart type. And I'm going to make my Excel window a little bit smaller so that we can see what's going to happen here. So to change chart type, if I go to XY scatter, this is always a good one to do for these types of data. I can go over and I can choose a scatter plot. I'm going to choose a scatter plot that uses the lines. And so basically it's going to plot every point and then it's going to connect them with lines, but it's not going to show a dot for every point. So like if I went to the scatter plot over here, scatter, it creates what looks like a really thick line, but that's because each dot has been placed with a marker there. So I'm going to do change chart type, scatter, like I originally said, and go to this line. And that looks a lot like what I had in my Google Sheets. The downside is it goes to 6, and I really only wanted to go to 5. So in that case, I can go down here like I originally wanted to do. I can double click on the axis. It'll bring up this format axis. And then I can now change my units. So I can say I want my maximum unit to be 5. Okay. Now, depending on how you do that, sometimes when you bring things in there and you do the steps that I just did, you might end up getting not only the curve you want, but you'll get this weird line that connects the end back to the beginning. If that happens for you, I want you to right click on your chart and go to select data. And that will bring up a dialog box that looks like this one. And when it says show empty cells as, change it from 0 to gaps. And that happens when you pull in data and the chart has been configured to chart a data range that is larger than the data range that has actually been populated in the spreadsheet. And in Google Sheets, when that happens, by default, it puts gaps in there. But in Excel, by default, it treats those as zeros. And so if you have gaps that happen after the end of your spreadsheet, if it happens to be charting those, it's basically going to treat them as if they're zeros, which means it's going to connect the end back to the beginning here. So if you ever plot to bring these things back in, you've got a line there, then that's what you need to do. And that's what's going to happen if you pull in your final spreadsheet that includes other time steps, other DTs, like I'm about to show you how to do in just a second here. So those are our tips there. You click on the chart, you change the chart type. So you go to chart type here, chart design, change chart type. You go to scatter, choose the line scatter. And then if you get that weird diagonal line, which turns it into kind of like a bow and arrow type look, you can right click on this thing, say select data, and then when the select data dialog box comes up, say show empty cells as, and make sure that it says gaps and not 0. And then you've got an Excel spreadsheet that you can save and you can upload with your document. All right, now let's go back to the Google Sheets here to investigate one more thing. So in our Google Sheets here, we initially simulated a time step of 0.01. Now that might not be the best time step for our simulation. So we might want to then also try some alternative time steps to see if we've really converged on the true approximation, or if our approximation still has stuff left to be deserved. In other words, we know that this Euler's method only works if our time steps is sufficiently small, but we don't know how small it needs to be ahead of time in order for this to be a good guess. Like, usually what I guess is that I try to find the fastest thing in my simulation. So in this case, it's the time between births or reproduction events in these bacteria. And in this case, it's 3/4 of a minute. Well, I want to make that dt much smaller than 3/4 of a minute. I'm not sure that 100th of a minute is that much smaller. So maybe I need to do 1,000th of a minute. So let's do 1,000th of a minute and see if it changes this graph that much. If it doesn't, then maybe 100th of a minute is fine. And that's great because the bigger I can make my dt, the faster the simulation will be. But the smaller I make my dt, the more accurate the approximation is, but the slower the simulation will be. So what I'm going to do is I'm going to take this sheet and I'm going to first get rid of that download thing here. I'm going to rename this the dt equals 0.01 sheet. And then I'm going to take this thing and duplicate the sheet. And then I'll rename this thing dt equals 0.001. And I'll go up here and change this to 0.001. And what I see now is that it immediately changed the simulation because you can see the time now moves in steps of 0.001 here. But the chart stops at half a minute instead of going all the way to my 5 minutes. And that makes sense because I only have 500 rows of simulation here from my previous sim, but now each row only represents 1,000th of a step. Well, 500 times 500 rows of 1,000th of a second or 1,000th of a minute is only going to give me the half a minute. So I need more rows of simulation. So I scroll down here to the bottom and I see that it ends at row 509, which is at exactly half a minute. And if I say, well, I'd like that to go, well, how many rows do I need? Well, if my time step is 1,000th of a minute and I want to go to 5 minutes, well, I need 5,000 rows. But my first row isn't until row 9. So I need this to go until row 5,009. So if I scroll down here, I see, oh, it stops at row 1,000. So I need to add, I'm going to say I'm going to add 4,010 more rows to the simulation, or to the spreadsheet here. And now I can see, aha, row 5009, that's where I want it to stop. So I'm going to click there. I'm going to scroll up until I get, I may want to just use my scroll handle here, scroll up until I get to the times that are populated in. And if I just hit shift and then click on one of these cells that has a formula in it, then I can use that hotkey on Windows machine, Control D, on a Mac, Command D, and that will then fill down all the way to row 5009, which lo and behold ends at 5 as I want. And then I can use my little trick where I highlight across here, I take the fill handle, and instead of filling down all the way like I might want to do, or I could do, I'm going to just double click on that. And Google is smart enough to know that it will go all the way to the end here to match this time column over here. I don't know if you noticed when I double clicked on it there, if you compare it to when I double clicked with the slightly bigger time step, it kind of took a little bit longer to complete. That's what I mean, where you don't want to make your time steps really, really small, or else it's going to take Google or Excel or Vensim or whatever a really long time to finish your simulation. So that's why we kind of want this sweet spot where you're not too small, but not too big. All right, now let's see what happened to the plot. All right, so Google was smart enough to know that to add to this data series so that it didn't still stop at half a second on where, the 509th row. It knew that this chart originally was charting all the way to row 5009. I just filled my 509. I just filled 509 all the way down to 5009 and automatically extended the data series. Now, if for some reason that doesn't happen to you, and this can happen in Excel as well, if I am to double click on this chart, it has data range here. And notice that this data range says A8 to B5009. That there, if I were to click on this little select data range, I can now select a different data range, or I can manually type it in. And so if it's stuck at saying A8 to B509, you can manually type in 5009 and it'll now properly fill that data in. So let me just show you as an example. If this was 509 like it was originally, I can go here and change it to 5009 and it fills that out properly. That looks good. All right, now I'd like to also see, so when I look at that, if I put my mouse on here and I follow it all the way up, it ends around 148. If I go to the 0.01 case, which is slightly smaller or larger time step, it ends around 144. It's not that different. It's a little different, but it's not that different. And so I'm going to see, well, if I'm okay with that level of approximation error, maybe I can make DT a little bit bigger. So, and that would make my simulation run faster. So let's just test it out and see. I'm going to then go and duplicate my DT tab again. This time I'll drag it over to this side, rename it to DT equals 0.1, change the DT to 0.1. Now notice now that my chart goes off the charts, so to speak. It is now very, like the bacteria look like they get very large, but it's only plotting the first 5 minutes here, and it looks pretty flat. The reason that happened is that I'm plotting 509 rows of the sim, but the sim now, every step or every row is now a 1/10 of a second instead of 100th of a second. So instead of needing 509 rows, I'm only going to need 50 rows. So if I go down here and I find row 59, that's the last row that I need. So I'm going to go to row 60. I'm going to go down to the end of the sim here at 509. And then I'm just going to delete. And so now I get my chart here. And it looks like it has the same shape as the other 2 charts. But if I look more closely, by dragging my mouse along these points, I can see it ends at 117. That is a lot less than the 144 that was here and the 148 that was here. Now, to try to understand what's going on here, I'm going to go to one order of magnitude bigger on my DT to really amplify this effect. So I'm going to do this. I'll say duplicate. I'll change drag that over. I'll change this to dt equals 1. And then from here, I'll change the dt to a whole second. Now, because I only need to go, or sorry, a minute, whatever my time units are, to 1 time unit, I'm only simulating up to 5 time units. All of the rest of these I can get rid of. And so now it goes to 5 minutes as expected. But if you look, if I click on this, if I see it, the curve here ends, let me bring that back, see if I can bring the mouse over here, at 32. So after 5 minutes, only have 32 bacteria, not 144. And if I look really carefully, there are corners, like it's like a straight line from 0 to 1, and then it rotates up, and it's like a straight line from 1 to 2. It rotates up a straight line to 3, a straight line to 4, and there's a really strong corner at 4 as it rotates up. So it keeps changing the angle here, but you get these straight lines. And we're really starting to see the artifacts of Euler's method here, where it's approximating the derivatives at every time step, and then it's pretending like the derivatives don't change across the time step, and then using those derivatives from the previous time step to predict where we're going to be at the next time step. Now, in this case, these are bacterial events, and we're saying that every bacteria reproduces on average every 3/4 of a minute. Well, that's less than our time step. So when we jump from 0 minutes to 1 minute, we've jumped over a bunch of reproduction events, which would have contributed new bacteria that would have started reproducing. So the only bacteria reproducing between 0 and 1 here are the ones that were at 0. But there are bacteria that are reproducing in the middle here that we didn't catch. We didn't catch any of their reproductives either. And so because of that, we're undercounting the number of reproduction events. And so that's why for this growth example, then this dt equals 1 is going to be much lower than dt equals 0.1. So it went from 32 to 118, which is itself lower because it's not a great approximation, to the 0.01, which is at 144, which is a little bit lower than the even better approximation of dt is 001, which is at 148. And so this tells me that none of these approximations are perfect, but as I get smaller and smaller and smaller, then the graph converges on a certain graph, and that graph is going to actually be a graph of the solution to this differential equation if I were to solve it mathematically and then plot that formula solution that was out. All right, so that's basically it. I've shown you how to simulate for multiple time steps, how to chart all of those different things. The only thing that I might show you now is if I wanted to download this as an Excel spreadsheet, just like I did before, I'd like to show you that little pitfall where you get that kind of bow and arrow thing for some of those plots. So if I download this as an Excel spreadsheet, so I'll download it as it's now got a 1 because I've already got one that's named that. So I'll download it as a second one there. And I'll open my new spreadsheet up in Excel. I'll make it a little smaller to bring that in. And for the dt equals 1, this looks pretty much like it did for the Google Sheets example, but for the dt equals 0.01 doesn't look so great. So I'm going to click on that, go to my chart design. For the chart type, I will go down to, and I'll make my Excel a little bit narrower so you can all see it. For my chart type, I'll go to XY scatter, and I'll select this line scatter here. And here's that bow and arrow effect that I was talking about. And that's what you want to avoid. So I'm going to right click on that. I'll go to select data. I'll pull this over. I'll say show empty cells as gaps. And when I do that, it gets rid of that bow and arrow. I can now double click on my time axis, change it to going up to 5. And there you go. That's a good looking plot there, which I could copy myself. So I could go to edit, copy, and I can now bring it into my Word document where this chart was, and I could go down here and paste it in. And there we go. I got the Excel formatted chart here. And there's the Google Sheets formatted chart. And so there you have it. That's how to do numerical integration in Google Sheets and a little bit in Microsoft Excel. And that's how to convert your Google Sheets documents into a little bit nicer looking Microsoft Excel documents when you have charts in them. Hopefully that is helpful for you as you're doing your homework and generally trying to understand the system dynamics modeling tools and what time step is doing behind the scenes.